if you have a point and a vector in 3D space, there is only one unique plane that contains that point and is orthogonal to the vector. And what I mean by that is, I mean, this might be kind of obvious, but what I mean by that is like, if where my fingers are touching this pen at the very bottom, if that's my point in space, right, I can move that anywhere in 3D space, and the direction and really the direction of this pen is the vector that I'm talking about, so I can choose a point in space and a vector just by moving this pen around. There's only one plane that contains that point and is orthogonal to the vector. So when I say a plane is orthogonal to this vector, I mean that the vector makes a 90 degree with every vector inside the plane. Does that make sense? 90 degrees? You look at it on the side, you can tell better. But that's what I mean by that first theorem. The standard form equation for a plane, and you should know the difference between standard form and general form. I'll tell you about general form in a minute. But the standard form is this. It's an equation where I have a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. A, b, and c are constants. X, y, and z are variables. X naught, y naught, z naught. That is a coordinate triple that describes the point in space that we're talking about. And ABC is going to be the entries of the vector that's orthogonal to your plane. And so this sort of idea of like you can describe a plane using a point and an orthogonal vector is important for constructing the standard form equation for a plane. But this is something you need to memorize. In fact, all that would be good to memorize. Yeah?
Can you share this slideshow with
Can I do what?
Can you put the slideshow in the middle?
Yeah.
Thank you.
Yeah, eventually. Maybe after class. And so one thing we can do is we can go to geogebra.com and try to graph the plane that passes through the point 3, 2, 1 and is orthogonal to the vector 1, negative 1, negative 5. So what that's going to look like is 1 times x minus 3 plus negative 1 times y minus 2 plus, gosh, did I say 5 or negative 5? Negative 5 is the vector. See, I hate GeoGebra. It is the worst website. Desmos is so lovely and easy to use, but do you know what happens? Like as soon as I click away from GeoGebra, it just like throws random crap in that because it thinks, you know, oh, I need to complete what I started without my input. It's like, no, just get rid of all that.
Dr. Mark, have you used Topplot 3D?
Nope. Is it better?
Yeah.
Okay. I'll have to try it out. Wait, no, minus 3. So minus 5 minus 3 equals 0. Now, let's try zooming out again and see if we see it. Okay. There it is. That's my plane. And so that plane passes through the point 3, 2, 1, where the x-coordinate is 3, the y-coordinate is 2, the z-coordinate is 1. I thought it would. Let's diagnose what's happening wrong here. It should be 3, 2, 1. Oh, okay, sorry, this should be a 1. Boop. There we go. Now we can see that that point is sitting there on the plane. And then the direction of the plane you get to choose but it has to be orthogonal to the vector 1, negative 1, negative 5. So that's where the constants come from here. Okay. Now, what did you say? It's called CalcPlot 3D. That's the name of the website, just like that, CalcPlot 3D. Maybe an implicit surface? Yeah, that's what I want. Okay, so my equation here would be x minus 3 minus 1 times y minus 2 minus 5 times z minus 1 equals 0. Let's see if that works. It does. Ooh, that's a little bit disorienting. If you try to like grab it and move it around, it's like, it moves a lot faster. Yeah, that's different. I'm not gonna say if it's better or worse than GeoGebra, but like, I kind of like how the z-axis stays like pointing upwards on GeoGebra if I drag this around. This feels more natural to me, maybe just because I use it all the time. But this is just a little bit weird because z doesn't always point up. Okay, well anyways, you got options. All right, so then this is the general form equation for a plane. And we can always take an equation that's given to us in the standard form and rewrite it in the general form. You just got to do some distributing and some collecting of the constant terms, and you can eventually get looking like this. But the a, b, and c are the same. The a, b, and c are still the entries of the normal vector, only instead of having the points x naught, y naught, z naught, according to some point that belongs to the plane, you just collect all of those constant terms inside that d term. And so there's only one general form of equation for a plane. There's a whole bunch of different standard form equations for the same plane because a plane has a whole bunch of points. So just choose any point along the plane and it works. But there's only one general form because this is just the simplified way to write it. So by the way, whenever I talk about a vector that's orthogonal to a plane, we call that a normal vector. And this is a very confusing thing to say, in my opinion, because you should know a normal vector is not the same thing as a normalized vector, right? A normalized vector is the same thing as a unit vector. A unit vector is a vector that has a norm of 1. And so if you normalize a vector, you rescale the vector so that has a norm of 1, but it points in the same direction. But you should know that normal does not mean normalized. Normalized has to do with changing the length of the vector. But a normal vector is just saying I'm orthogonal to a plane or a surface. So you should know the general form of equation for a plane. And then let's do exercise 4 together. Let's write the general form of equation for the plane that passes through the point 3, 2, 1 and orthogonal to the vector 1, negative 1, negative 5. Let's try that. And step number 1, we're going to start off writing the standard form. And we've already done this a couple of times now, but the standard form for this plane would be 1 times x minus 3 plus negative 1 times y minus 2 plus negative 5 times z minus 1 equals 0. And then after that, after you've written the standard form, then you can simplify. We're going to distribute the coefficients. and then you collect all the constant terms. So negative 3 plus 2 is negative 1, plus 5 is is positive 4. Yeah. And that's my general form right there. Okay. Is that pretty easy? Questions? Okay. So another idea for you to think about is any 3 distinct non-collinear points in space uniquely define a plane. If the points are collinear, this doesn't work, right? If they're collinear, that just uniquely defines a line, but lots of different planes could contain the same line. But if you've got 3 non-collinear points in 3-dimensional space, that uniquely defines a plane. There's only one plane that passes through 3 given points. I like to think about how a table with 2 legs would fall over, wouldn't be stable. Never build a table with 2 legs. But if you build a table with 4 legs, it always wobbles, right? It's never quite even. Table with 3 legs, it's just the right number of legs to be a table. So the tabletop is kind of like your plane, and your legs are kind of like the 3 points that are uniquely defining what the surface of the plane should be. So now let's find the general form of equation of the plane containing these 3 points. How do I do that? How do I find an equation for a plane that contains all 3 of these points? Mm-hmm.
And then your plane would have to be parallel to that.
That's true. So if I draw a vector between any 2 points, the plane will have to contain that vector, right? The vector would have to be parallel to the plane. Yeah, that's true. What I'm looking for is a 3-step process. And step number 2 is going to be write the standard form equation. Step number 3 is going to be to simplify, because we're looking for the general form. And if I have the standard form equation, I can simplify it to get the general form like we just did in the previous exercise. But step number 1, how do we find the standard form? Well, in order to write the standard form equation, I need 2 things. I need a point that belongs to the plane, and I need an orthogonal vector. Okay, so I've got a point. In fact, I could choose any one of these 3 points to be my point that belongs to the plane, the one that I use for the standard form equation. But what I still need is I need to find an orthogonal vector. And this is how you find the orthogonal vector. And again, I could have called this the normal vector instead of orthogonal vector. That would be, I guess, a better way to say it, is find the normal vector. And in order to do this, I need to first find the vector AB, which is just the points B minus the points A, and then the vector BC, which is just going to be the point C minus the point B. Or I could say call it AC maybe. I don't know. I'm making this up. So now if this is like A, B, and C, I've got a vector pointing this way. That's my vector AB, and a vector pointing this way. That's my vector AC. And then if I want to have a vector orthogonal to the plane, that vector needs to be orthogonal to both the vector AB and the vector AC. Can you think of any kind of operation we've learned about that gives me a vector orthogonal to two input vectors? The cross product. Yeah. That's one of our cross product properties, is that the cross product of two vectors is always orthogonal to the two vectors that you're multiplying, that you're using. So anyways, let's do it. Let's figure this out. So B minus A is going to be the vector 1 minus 1, 4 minus 2, 1 minus 3. And C minus A is going to be the vector negative 2 minus 1, negative 1 minus 2, and 0 minus 3. Now, the cross product has a really big, annoying formula that you have to memorize. We're going to use it 1,000 times this semester. So we write UV minus UV, UV minus UV, UV minus UV. And then we write 2, 3, 1, 2, 3, 3, 2, 3, 1, 1, 3, 1, 2, 2, 1. And for us, U2 times V3 is going to be 2 times negative 3. U3 times V2 is going to be negative 2 times negative 3. U3 times V1 is going to be negative 2 times negative 3. U1 is 0. U1 is 0, and then U2 times V1 is 2 times negative 3, which is negative 6. So the normal vector, which is the vector orthogonal to my plane, the one that I'm looking for is negative 12, 6, 6. And it doesn't really matter what the norm of this vector is. Like, I could use negative 12, 6, 6, or I could be a little bit less extra about it and call it negative 2, 1, 1, right? Just divide all the entries by 6. That does not change the direction of this vector. It just changes the magnitude or the norm of the vector. And all I really need is a direction to know which direction my plane is facing. All right, now I can write the standard form equation, and the standard form equation is going to be negative 2 times x minus, we'll use the point A, because like, why not? You could use B or C, but A is nice. X minus 1 plus 1 times y minus 2 plus 1 times z minus 3 equals 0. And like I said a moment ago, I could have used negative 12, 6, 6 here. But then when I wrote down this equation, I would think to myself, oh, this would be a lot simpler if I just divided both sides of this equation by 6. And 0 divided by 6 is still 0. So I don't really need to do that. I can just go boop, boop, like that. Okay, and then simplifying means I distribute the negative 2, and I've got a plus 2 here, a minus 2 here, and then minus 3 equals 0. So that's the general form. And let's try it out. You know, I always say on your homeworks you should be checking your answers, because I don't give you like an answer key. But here's how you check your answer. We take negative 2x plus y plus z minus 3. And try that here. Negative 2x plus y plus z minus 3 equals 0. That should give me a plane. And I'm hoping that this plane contains these 3 points. 1, 2, 3, 1, 4, 1. One, 4, 1, and negative 2, negative 1, 0. Okay, let's take a look. We got them. See how my nice purple plane goes through my blue balls here. My 3 points. All right. Questions so far? No? Two distinct planes in 3D space are either parallel, right? I could have two parallel planes that never, ever, ever intersect each other. Or if they do intersect, if they're not perfectly parallel, then they intersect along a line. The intersection of two planes is a line. One question you might have, I don't know what, calculus theory doesn't have a lot of like real life applications. I'll say that. But suppose there was some reason why you wanted to know the angle between two intersecting planes. This is how you would find it. It's this formula right here. It should look pretty familiar. Because if n1 and n2 are the normal vectors to plane number 1 and plane number 2, then this formula is the same as the angle between the normal vectors. The angle between the planes where they intersect and the angle between their normal vectors is the same. So, I'm going to draw you a little picture because you might be wondering, why does that work? Imagine this is plane 1 and this is plane 2. And I'm looking down on these planes like a bird's eye view above their line of intersection, so that their line of intersection is now just a point. And you can always sort of rotate your camera so that you can look down the line of intersection from your perspective. So the planes just become lines. And what I really care about, what I'm asking this question about is, what's this angle right here? That's the angle of intersection between the planes. So then, each one of my planes has a normal vector that makes a 90-degree angle with the plane. And so this is n2. Then I've got a normal vector here that makes a 90-degree angle with plane 1. So that's n1, that normal vector. And if I were to get a straight line and extend these normal vectors out until they intersect each other, let's think about this. I'm going to name this angle here phi. And I know theta plus phi has to be equal to what? 180 degrees. Because theta and phi are complementary. Together they form a straight line. And what I've just enclosed here between these orange line segments and the purple dotted line segments is a quadrilateral. And the interior angles of a quadrilateral have to add up to 360. And so I've got a 90-degree angle because of the normal vector, another 90-degree angle because of the normal vector, plus I have the angle phi inside that quadrilateral. And then I have to add one more thing to reach an interior angle sum for this quadrilateral of 360 degrees. And so that blank here has to be theta. It has to be theta, because if I subtract 90 from both sides, or I should say if I subtract 180 degrees from both sides, then theta plus blank equals 180, then it has to be, or sorry, I said theta. I meant phi plus blank equals 180, that has to be theta. And so the angle between the normal vectors is the same as the angle between the planes. What would it mean if the normal vectors have a dot product equal to 0? Yes. A dot product of 0 means that the normal vectors are orthogonal to each other. What does that mean for my planes if their normal vectors are orthogonal? Then the planes would be orthogonal to each other. Yeah, if their normal vectors are orthogonal, the planes are orthogonal. That means that angle theta must be 90 degrees. The angle between the planes is 90 degrees if n1 dot n2 is equal to 0. What does it mean if n1 equals k times n2, where k is just a scalar? That would mean n1 and n2 are parallel. And that means theta is 0. And that means the planes themselves are also parallel. Okay, you feel good about that? Okay. Find the angle between the following two planes. So if I have an exercise like this one, let's call this one P1, call this one P2. Let's make n1 be the normal vector to plane 1. And what should the entries be for n1?
1, -3, 1.
1, -3, 1. And n2, what should the entries be?
2, 3, -2.
Very good. 2, 3, -2. And so to find the angle, I have to take n1 dot n2 divided by n1 norm, n2 norm. n1 dot n2 is going to be 1 times 2 plus -3 times 3 plus 1 times -2. n1 norm is going to be 1 squared plus -3 squared plus 1 squared square root times the norm of n2, and the norm of n2 is going to be 2 squared plus 3 squared plus -2 squared, and then take the square root. And altogether in the numerator, I've got -9 square root of 11 times the square root of 17 I don't know what 11 times 17 is. That'd be 187. And 11 is prime, 17 is prime, so I know there's no way to simplify that square root. And then I would just have to take the arc cosine of that, right, to get theta. And you can just plug that in your calculator. Okay, makes sense? Kind of already done that before when we talked about the dot product last week. Or the week before, I guess, because last week we had Labor Day. The line of intersection of two planes must be orthogonal to the normal vectors of both planes. What is that saying? So I talked about how if two planes are not perfectly parallel, then where they intersect is a line, like the binding on this packet would be the line of intersection of these two planes. And then that line has to be orthogonal to the normal vector of this plane and this plane. And there's really not a lot to prove here. What I would say if someone asked me for a proof is I would say the line of intersection belongs to both planes the orthogonal vector n1 is, or sorry, I should say the normal, I guess, because I use the word normal. I'm trying to use the word normal. The normal vector n1 is orthogonal to every vector in plane 1, and the normal vector in 2 is orthogonal to every vector in plane 2. Right? So that's kind of, it's just a matter of understanding the definitions is basically what I'm trying to say. Is like, we say n1 is the normal vector because it's orthogonal to everything inside of plane 1. We say n2 is the normal vector because it's orthogonal to everything inside of plane 2. The line of intersection belongs to plane 1, and the line of intersection belongs to plane 2. So it has to be orthogonal to both. Sorry, there's not a lot there to work out math-wise. It's just a matter of, do you understand the definitions of what we're talking about? So, exercise 7. Find the parametric equation of the line of intersection of these two planes. What should we do here? I'll let you think about this for a minute. What would I do if I wanted to write a parametric equation of the line of intersection? It's been a while, but remember that a parametric equation of a line looks like this. It looks like you have some point that belongs to your line, plus you have a parameter times a vector parallel to your line. I don't know what we want to call this vector. I'm going to call this vector I don't want to use the letters ABC because you're using the letters ABC for the entries of a normal vector, and this is not one of the normal vectors, right? So I don't know what I should use for letters here. I've got to make something up. Let me use L for line. This will be L1, L2, L3. But my final answer to this problem is going to look something like this, because that's what the parametric equation for a line looks like. The real question, though, is how do I find what is going to be my x naught, y naught, z naught? And how do I find out what is going to be my L1, L2, L3? In other words, how do I really flesh out this equation for the line? There's going to be a few steps here. Number one, define the normal vectors. For each plane, right? Plane 1, plane 2, they're both going to have a normal vector. Step number 2. We just talked about how the line of intersection between two planes has to be orthogonal to the normal vector of both planes. What is an operation I can do to get a new vector orthogonal to two given vectors? The cross product. And so this L1, L2, L3 vector is supposed to be a 2. That could just be N1 cross N2. Because the cross product is going to give me a third vector that's orthogonal. And I just need any old vector that's going to be orthogonal to both of those normal vectors so that it can be parallel to my line of intersection so that it can fit in right here. Then the last thing I need is x naught, y naught, z naught. There are a lot of points along this line of intersection. And so the idea is going to be basically choose one of those points arbitrarily, right? Like you get to decide what do you want x naught to be. And then the last thing we need to do is solve a system of equations using the plane equations. That's our plan. So let's see what that looks like. N1 is going to be the vector with what entries? Perfect. 1, -3, 1. N2, the vector normal to the second plane, has what entries? 2, 3, -2. Okay, so when I take their cross product, what I'm thinking about is 2, 3, 3, 2. So I don't know. Maybe I shouldn't try to do it in my head. I hate cross products. Cross products are the worst. Because even after years of practice, I still can't take a cross product like mental math style. I've got to write it out every time. So 2, 3, 1, 2, 3, 3, 2, 3, 1, 1, 3, 1, 2, 2, 1. So let's say the U part is going to be N1 and the V part is going to be N2. So whenever I say u2 v3, I'm talking about negative 3 times negative 2. Then u3 v2 is 1 times 3. And u3 v1 is 1 times 2. u1 v3 is 1 times negative 2. u1 v2 is 1 times 3, and u2 v1 is negative 3 times 2. Be negative 6. Negative 3 times 2 is negative 6. So their cross product is going to be 3, 4, 9. And that's a vector that I can use in my parametric equation. So we're good for that part. The next step is kind of going in a different direction. We have to arbitrarily choose some x naught. So pick out a number you like for the number, for the coordinate x, for the x coordinate x naught. And so let's just go ahead and choose x naught equals 0, because I think that's a nice number. Very well-rounded. And then what I mean by step number 4, solve a system of the two plane equations. What I mean by that is bring these guys down. I'm going to plug in x equals 0, and I get the equation negative 3y plus z plus 5 equals 0, and the equation 3y minus 2z minus 1 equals 0. So I get a system of two equations, the two equations that I get from the planes. And I've already plugged in x not equals 0, or just x equals 0, because I get to choose one. In fact, you could decide to choose y or z arbitrarily and solve for x, but you know, it's a degrees of freedom thing. You have 3 variables, right? 3 x, y, z variables that aren't defined yet, but you have 2 equations. And so 3 variables minus 2 equations. You have 1 degree of freedom. That's why we can choose one of the variables. Okay. So it's up to you how you want to solve this system of equations. I would just add these two together, because I see if I add the first equation plus the second equation, I get to eliminate y. The y variable just goes away if I add them together. So negative 3y plus 3y is 0y. Z plus negative 2z is negative z. 5 plus negative 1 is 4. 0 plus 0 is 0. And what I get is that z is equal to 4. So we got x naught equals 0, z naught equals 4. Lastly, pick one of those equations, doesn't matter which one, and now we solve for y, because we know z has to be 4, and that means y has to be what? 3. Cool. So now I've got x naught, y naught, z naught, and I'm ready to write my final answer. And my final answer is the parametric equation for the line of intersection between the planes. And that's going to be 0, 3, 4 plus t times 3, 4, 9. And that's what your answer looks like. So to check your answer, let's try this. X minus 3y plus z plus 5. X minus 3y plus z plus 5. And my next plane was 2x plus 3y minus 2z. And then I should be able to see the two planes, and I should be able to see their line of intersection where they intersect each other. And then the last thing I want to try to graph is this parametric equation, which is going to be 0 plus 3t, comma 4t plus 3, and 9t plus 4. Okay, and then you can check on GeoGebra that the new black line that we define parametrically is the same as the line of intersection between the planes. Everybody sees it? All right. It was a long problem. Okay, the shortest distance from a plane to a point. What if you know a plane in space and you know a point in space and you want to know what's the shortest distance from the plane to the point? The shortest distance is going to be the path along straight orthogonal path. Let me draw a picture. So imagine this is my plane. This is the point. There's a lot of different paths that you could go on from the plane to the point. That's not the shortest one. Not even this is the shortest one, but the very shortest one is going to be making a direct 90-degree angle with the plane itself. So that's what I'm talking about. It's the straight orthogonal path from the plane to the point. Okay, so if we want to find this distance, find the coordinates of any point P in the plane. And so maybe this point over here is point P. It could be any point you want. But then we're going to find a vector that goes from P to Q. And so there's our formula for our PQ vector. Then, since we know what the plane is, we can find a normal vector that's orthogonal to the plane. And we're going to find the projection of PQ onto N. And you have to remember your projection formula. My projection formula is PQ dot N over N dot N times N. So that's going to take just the component of the PQ vector that's in the direction orthogonal to the plane. And once you find the norm of that projection, that's the distance. Because this part is the projection. And the norm just tells you how long it is or how far you have to go. So that's something to remember. The next theorem says the distance d between a point Q and the plane passing through point P orthogonal to vector n is equivalently just the vector PQ dotted with n hat. So notice n hat, do you remember what the hat means? Is a unit vector, so it has to be normalized. And then you take the absolute value. I imagine the proof is pretty straightforward. I'm just going to try starting with this, the thing that we talked through already. And if I have the norm of the projection of PQ onto N, that's the same thing as the norm of this whole mess. And this is a scalar times a vector, right? And so whenever I take the norm, it's really just taking the norm of this vector and the absolute value of this scalar. Only you also know, you remember that n dot n is the same thing as the norm of n squared. It's one of our properties of the dot product. And so this would be like having PQ dot product with n divided by the norm of n, absolute value. Because there's a norm of n in the numerator and there's two norm of n's in the denominator there. And so one of them cancels. And then remember that n hat means it's a normalized version of n. So that's a formula for n hat. And I see n over n norm here, so that must be PQ dot n hat. And that's a formula for the distance. The distance between a plane and a point Q out in space that doesn't belong to the plane. Okay, so find the distance between the point 1, 3, negative 4 and the plane 3x minus y plus 2z minus 5 equals 0. I'm going to start doing these pretty fast because I see we've got about 11 minutes left in class and I want to make it through a few more pages of notes if possible. So let's do this quickly. Number one, we need to find any point in the plane. So that means I get to choose what I want for x and y. And I'm trying to do this as easy as possible. I'm not trying to make it harder on myself. So I'm going to choose x equals 0, y is equal to 0. And then this plane equation becomes 2z minus 5 equals 0. And I can solve for z. It's going to be 5 over 2. So my point P is now the point 0, 0, 5 over 2. Step number 2. I have to find the vector PQ, which is going to be Q minus P, which is going to be 1 minus 0, 3 minus 0, and negative 4 minus 5 over 2, which is like negative 8 over 2 minus 5 over 2, which is negative 13 over 2, right? Correct me if I'm about to get that wrong. We need to find n, which is the vector normal to the plane, which is going to be 3, negative 1, 2. I get that from the plane equation. And then my my formula for the distance is the absolute value of PQ dotted with n hat, which is another way of saying like PQ dotted with n divided by norm of n. So let's find the PQ dotted with n part. And that would be 1 times 3 plus negative 1 times 3 plus negative 13 over 2 times 2. So it would be negative 13. Divided by the norm of n. The norm of n is going to be the square root of 9 plus 1 plus 4. So it's the square root of 15. So the distance is 13 over square root 15. Or you could also say 13 square root 15 over 15 if you want to, but it doesn't matter. That's fine. Okay, so it's a matter of knowing the formula, knowing what to do. Again, step number 1 is a degrees of freedom thing. With this equation, I've got one equation, but 3 unknown variables. So that means I have 2 degrees of freedom. It means I get to pick out 2 of the variables. You don't have to choose x equals 0, y equals 0, but I think it's the easiest way to choose. And that's how you do it. Let's see what else we have. Find the distance between 2 parallel planes. If this is the problem statement, then you don't have to test the angle between the planes. Just agree with the problem and say, yeah, we'll assume these are parallel. And if they're parallel, that means step 1 is choose any point in plane 1. And step number 2 is find the distance between the point Q and plane number 2. Parallel planes, by the way, always have exactly the same shortest distance between them, right? They never get any farther apart, they never get any closer together. And so you don't have to worry about choosing a specific point. You can choose any point. That means you pick an arbitrary x and y, and then you calculate the z using the first plane equation. And then we've already done this. We've already found the distance between a point and a plane. And so you follow the same procedure after that. Exercise 10 says, state and prove the following formula for the distance between a point Q and a line parallel to the vector u containing point P. And so if you were given a parametric equation for a line, you look at the parametric equation, you can see a point that belongs to the line, and you can see what a vector is that's parallel to the line, right? And then you can do this distance thing. So how would we come up with this formula? Let's draw my point Q, and let's draw my line. And this line has a point P, and the line is parallel to a vector u. Let's call this vector u. And what I would really like to know is what is the shortest distance, like right here. Obviously the shortest distance is going to be along a path that is making a 90-degree angle with my line. And then what I need to complete this picture is a vector PQ. That would be not too bad to calculate. And then I'll scooch the same vector PQ over here. And I'm going to scooch the same vector u and make a copy of it right here. And now I have a parallelogram. And that might not seem like a big deal. But the area of the parallelogram is going to be equal to the cross product between the sides vectors, right? The norm of the cross product between those sides. Well, what else is the area of the parallelogram? The parallelogram is basically two triangles, if I do this diagonal right here. And the area of a triangle is 1/2 base times height. So the area of the parallelogram is just base times height. The base is norm of u, and the height is the length of this orange dotted line. And the length of the orange dotted line is the distance we're trying to find. So now solve for the distance here. And we get u divided by the norm of u. But you could also call that u hat if you want to. You can do that if you want, if that's easier to calculate with, or you can do u hat and calculate the normalized vector first. A lot of times with these calculations, it's actually this formula that's faster to calculate with, because when you normalize a vector, normally the entries of that vector become like fractions in the best case scenario, like 2/5, 4/5, 3/5, or even in the worst case scenario, they're like fractions that involve square roots. You end up like with 2 over square root of 11 or 3 over square root of 11. So a lot of times I don't like to divide by a norm until the very end of the calculation, but that's a quick proof. You would draw a parallelogram like that and work it out. And then I'm not going to have time to show you how to find the distance between the point and the line, but finding the distance between the point and the line means using that formula that you're given there.